Hello, everyone. Just making sure. Okay.
Okay.
Yeah, thank you. I was a PhD student of Paulo. So after this, if you have questions, Paulo is there, so you can ask um, more questions from Paulo. And the talk is about complexity synchronization. So I should define what we mean complexity, what is complex system. And here I just show three different signals that we have, like this is EEG from brain, and this is respiration from lungs, and ECG from hearts. And you can see that they are different signals. And the question is how we can see that they are interacting. It's not that they are, hello? It's not. Do you hear me?
We
Do you hear
don't.
me? Do you hear?
We hear. Okay, we try again. Start to speak.
Yeah, so yes. So I start from the beginning. I start from the beginning.
Okay, start again. Share
Yeah.
the screen.
Okay. So do you see now? So do you see now?
Okay, okay.
Okay, there's a delay, I guess. Okay. And so we are looking for a measure to show the interaction between brain, heart, and lungs. And as you can see in this figure, the signals have different structure, and it's hard to see that they are actually interacting. By complexity, we mean the index of a power law distribution. For example, so to be specific, we are looking to the distribution of the time distances of the events, and we call that temporal complexity. Here, for example, I have the strides. So if you walk and measure the time distance between the strides and look at the distribution of those times, it's not a Gaussian, it's a power law distribution, and the slope of that distribution, the slope of that power law is a measure of the complexity. And the other question is why, if you have systems and they are complex, why their complexity synchronizes. And here there was one example, the experimental work, that one patient, the elderly who couldn't walk properly with the Parkinson's disease, was paired to walk with a healthy person that was a nurse for some weeks. And over weeks, the complexity of the elderly improved, and he could walk, he could recover his walking pattern. So this shows that actually the complexity of this elderly, the complexity of the walking of the elderly improved by training. So complexity can change over time. The method that we use and we introduce to measure the complexity is diffusion entropy. So we call that diffusion entropy analysis. And here, for example, I show the ECG data from the heart. And what we do, we introduce these stripes. So here I have 10 stripes, the horizontal lines. Here on the top right panel, I have the zoom in of the same signal from this part. And if you look at the signal now with the stripes, whenever the signal passes from one stripe to other, so from one state to other state, we call that one event. So there's these red dots are the events. You can see here that there are one event here, one event here, Then there are plenty of events here. Then again, there are small events, etc. So by that means the system is stable for like this time, and then it moves to other state, and we are interested in these events. So for each event we assign one, and we create this panel B that represents the events. We forget about the original time series, and now we focus on the statistics of this new time series of the events. By that, we create a diffusion time series. That means just adding up these events. So we create this time series. The next step is to create a statistic of only this time series. We have to slice this to pieces with size W. So we're trying to make statistics. So here I picked W100, and after cutting, we move all these signals to start from origin. Of course, they end up at time 100. That's W. And we can look at the distribution of these points. So let's say the distribution will look like this. This was for 1 omega 100. We can actually do that for variety of W size. And I can collect all the distributions of W and X. By collecting those distribution, I can evaluate the entropy. So this is the Shannon entropy. So by knowing the Px of W, I can calculate this. And if there is a scaling, this is the if there's a scaling in the time series, that would obey this function, this relationship. This just says X is proportional to W power to delta, and delta is the scaling. So the W is as a dimension of time. So you can say X is proportional to time to delta. So if delta is 1, that's ballistic. So X is proportional to T. And if delta is 0.5, that's random walk, etc. So this delta can be a number between 0 and 1. So for the brain and biological system, you can see delta is very close to 1. When delta is 0.5, the process is random. And when delta is very close to 0, the system is having very extended times, means technically it's not changing at all. So using that technique, going back to the same figure, initial figure I showed you, so I have these very different time series. But if I use this method and if look at the statistics of the events, so means I put thresholds here, I extract the events here, and for this one, and same thing for here. And I look at the statistics of those events, I can, using diffusion entropy, I can actually measure the scaling delta. So here, if you put this p value in the definition of Shannon entropy, by very simple calculation, you can see that entropy is proportional to a scaling times logarithm of W. So means if you plot entropy versus logarithm of W, there will be a line, and the slope of that line will be the scaling. So here I just showed some results of these three different time series, and each of them will show a linear part, and the slope of that will represent the scaling of that. So it's helpful because now if I look at here is the 15 minutes of data that we had from participants during the neurofeedback training, and at the same time when they were doing this training, their EG, their ECG, and their respiration was recorded. What I did, I divided these 15 minutes to 13-second windows, and for every 30 seconds I measured the delta, the scaling. By that, so this background, these thin lines are for 64 channels of EEG data. What first thing that is obvious that the scaling of the brain is not constant. It changes over time. And if I do the same thing for respiration and for ECG, they change over, their scaling, their complexity changes over time. But on top of that, all of them are in synchrony. This is what we call complexity synchronization. It means their statistics are connected. So that was for real data. And the question was, can we such a thing for a model? Yeah, so, and I used the agent-based model. And here's the simulation I will show you. And there are two sort of agents here. So the triangles the triangles actually following the circles, so their benefit is in to be close to the circles, and for the circles they want to avoid the triangles, so they are competitive agents. And so you can think of these triangles like sharks and these circles like fish, artificial of course. So the coloring here shows is because if the agents have two ways of making decision. The decision is which direction to go. And if either they go back to their own past experience and make a decision based on their own, or they can follow the direction of the neighbor. So it's like Vixek model, but there is no control parameter. So by that simple rules, they interact, and this is the boundary condition. So it's a periodic boundary condition. So by running, I hope you can see. So this school of fish and the school of shark forms. And now I can look at the dynamics of system where the quantity I pick is the order parameters. So that's order parameter means how aligned this school of shark is. And the other time series is how aligned the school of fish is. So two time series, and I can look at the complexity of these two time series the same way I did with the data. By doing that, looking to the time series, again, I split that to small pieces, and for each piece, I evaluate the scaling. And you can see the scaling delta changes over time, but at the same time, they they improve their scaling, or they decrease their scaling. So we can see this complexity synchronization in the models as well. So in conclusion, we developed a tool that's diffusion entropy to measure the complexity synchronization between different parts of a self-organizing system. And the other thing is by this, we can actually study the complexity synchronization between humans and machines, because they are two complex systems interacting bidirectional. And by that, we can design machines that are more compatible with the complexity of the human, and so design machines that are like companion, trainer, and rehabilitator. And I want to thank Scott and Piotr for their contribution. Thank you.
Okay, thanks.